Welcome to Axis VM. In this video tutorial, we will cover the shell model described in the step-by-step tutorial available on the Axis VM website. We will go over the design and specific internal forces of the model, which will be designed under the Eurocode 2 standard. In Axis VM, create a new model. Set the model file name to reservoir, select Eurocode from the design codes, and set the units and formats to EU. For the first step, change the grid and cursor step settings from the Options menu. Replace each value under a cursor step with 0.2. With these settings, the mouse cursor moves in 0.2 meter steps. Close this window to create the geometry of the model. Select the Elements tab, then select the Elements toolbar and click on the Draw Objects Directly icon. Click on the Domain icon and in the window after the warning message, select the C25/30 concrete from the materials list. Close the window with OK. Then set the thickness to 250 millimeters. Click on the complex slab icon to draw the model. Firstly, we'll draw the side wall of the reservoir in the XZ plane. In the XZ plane view mode, choose the origin as the first point of the polygon. Move the cursor to the next point and click to define each vertex. From the origin, click 11 meters right and 0.2 meters down. Then down 0.4 meters, right 1 meter, up 3.6, left 12, and finally down 3 meters. Press Escape twice to quit the drawing function. Then change the view to perspective. In the perspective settings, set the values h equals 30, v equals 320, and p equals 0. Now create the parallel wall in the reservoir. Click on the mirror icon and select the entire domain with the All button. Click OK. In the window, select the Multiple mirror type and set all of the nodes to connect. After clicking OK, define the mirror plane with 2 points by setting the following 2 points. X equals 12, Y equals 4, Z equals 0. And then define the point X equals 1, Y equals 0, Z equals 0. Press Escape to finish. Now click on Zoom to Fit for a better view. In the bottom right corner, click on the numbering icon. Then check the node box. This will display the node numbers. To specify a slope for the watercourse, move the line between nodes 3 and 4 down by 0.2 meters. Do this by translating the line downwards as shown using the Translate icon on the left. In this example, a reference point will be used to define the orientation of the local z direction of the domains, and a reference plane will be used to define the x and y axes. Click on the reference point icon on the Elements tab, and click on the center point of the line between nodes 5 and 11. Then press Escape to exit the function. Now, in the Numbering Speed button, check the reference box. An R2 label will appear over the new reference point. Now create a reference plane. Click on the reference plane icon on the Elements tab. 3 points are needed to define a plane. Click on node 6, then anywhere between nodes 1 and 2, and then click on node 1. Press Escape to exit the function. Now define a domain to create structural surface elements. Click on the domain icon and then click on the perimeter lines of the following walls to select domain contours. Select the back wall, the bottom surface, and the front surface. And then click OK. In the new window, set the thickness to 250 millimeters, and then set the local X reference value to R3. Close the window with OK. A green contour can be seen along the domain boundary. Define the other wall elements. Click on the domain icon again and select the side wall of the watercourse. Click OK and then choose the shell element type. Set the local X reference to R3 and set the local Z reference to R2. Click OK and then create another shell element in the bottom of the watercourse as shown. In the domain settings, leave the references on Auto and click OK. Then check the display of the domains by clicking on the local System Speed button. Turn this value off along with the numbering of nodes. Now define ribs on the upper edges of the model. Click on Line Elements. Select the 4 top edges and then click OK. In the Line Elements window, click on the Cross-Section Editor icon. Click on the Rectangular Shape icon and then type in B equals 300 and H equals 600. Click Place and place the cross-section. Then click OK to close the cross-section editor. Now set the eccentricity to the bottom rib and close the Line Elements window with OK. Rib center lines will be displayed in blue and the contour of the rib will be yellow. Moving the cursor over a rib will display the element properties. The rendered model can be viewed in the rendered view mode. To define supports for the structure, click on the Surface Support icon. Click on the bottom 2 domains and finish with OK. In the window, change Rx and Ry to 1000. And then click OK. To define loads, click on the Loads tab. Click on the Load Cases and Load Groups icon. Rename the selected load case ST1 to Self-Weight. Then close the window with OK and click on the Self-Weight icon to define the load case. Select all of the elements and click OK. Dashed lines along the domain contours represent the self-weight. Moving the cursor to a domain edge displays the weight of the specified domain. Now create another load case by clicking on the Load Cases and Load Groups icon. Click on the Static Load Case button and enter Water as the name of the new load case. Click OK to close the window again and define the water load by clicking on the Fluid Loads icon. Again, select all of the elements and click OK. In this window, change Z1 to 2.7 meters and then set PZ2 to -35. Click OK to close the window. Now create a load combination by clicking on the Load Combinations icon. In the table browser, click on the New Row icon. Leave the default name and select User Defined Combination. Then enter 1.35 for the case self-weight and 1.0 for the water case. Click OK to close the window. Then, in the speed buttons, turn off Supports, Reference, and Object Contours in 3D. To create a finite element mesh, change to the Mesh tab. Before creating the mesh, turn off the load display at the speed buttons. Then click on the Domain Meshing icon. Select all of the elements and in the Meshing Parameters window, select the rectangular mesh type. Set the average mesh element size to 0.6 meters and click OK. When the mesh finishes, green points at the center of surface elements represent center points of the shells. In the speed buttons, uncheck Nodes, Surface Center, and Domains. Then turn off the mesh display. With this last step, we have finished the finite element modeling. To run a static analysis, click on the Static Analysis tab and then click on the Linear Static Analysis icon. When the analysis is done, the Static tab will be active, showing the displacement of the structure in the EZ direction. This will be displayed in the load case self-weight, displayed in the Isosurfaces 2D view mode. Click on the Numbering speed button and check Write Values to Surfaces and Min-Max only. To see the result for the water load case, click on the drop-down menu and change self-weight to water. Then select the EY result component. To hide the front wall of the reservoir for a better view, create a part. Click on the Parts icon on the left. Click on the New icon and then specify the name as 1. Then, in the XZ plane, select all of the elements and then unselect the front wall. Click OK and then close the Parts window. Then restore the previous perspective view. To find extreme values of horizontal displacements, click on the Min-Max Values icon. Select the EY deformation component and click OK to display the location of the maximum negative value. Clicking OK again will display the maximum positive value. Close the window with OK and select the load combination CO number 1 from the drop-down menu, and then select the ER resultant displacement. Click on the Result Display Parameters icon and set the display shape to deformed. Set the display mode to diagram and change the scaling value to 2. Close the window with OK. Turn on the Mesh Display Speed button and then change the display mode to the Hidden Line Removal mode. You can rotate the model to get a good view of each side. Now revert the view and go back to the result display parameters and change the display shape, display mode, and scaling to their previous values. Also revert to the wireframe view. Use the speed buttons to turn off the mesh display, and then change the displayed result component to the Surface Internal Forces MXD Plus component. For reference, the color legend shows boundary values of each color. You can adjust the number of boundary values by expanding or contracting the legend window. Now change the displayed result component to the Surface Internal Forces MYD- component. To specify sections for displaying the diagram, click on the Section Lines icon on the left. In the window, click on the New Section Plane icon. Provide the name 1 for the section, and then change the view to the XZ plane. Specify a section plane in the middle of the reservoir. And then, in the section line display mode, change the view to the YZ plane. On the numbering speed button, turn on Write Values to Lines. This will display some properties of the section. Turn off the section line display mode and change to the perspective view. Change the display mode to ISO Surfaces 2D and then select the Surface Support Internal Forces RZ component. This shows vertical reactions of the surface support. With this, we have finished the setup of the shell model. Thank you for watching. More details about the shell model, including an analysis of the required reinforcements, can be found on the AXIS VM website.